Welcome to the Aufbau Principle and the periodic table. So the Aufbau Principle says that as an atom is built up, Aufbau is the German word for built up. So as an atom is being built up, the electrons that we add fill the lowest available energy state. So here we have an Aufbau diagram showing the various energy levels and orbitals in there in the atom. So we have the 1s, the 2s, the 2p, the 3s, 3p, 3d, and so on going up. Know that they continue up past what's shown here, but this is enough to show most elements on the periodic table. So again, down here we have the L values. L equals 0 are the s, so you note that all of the s orbitals are here, all of the p orbitals are there, and again there is no 1p. All of the L equals 2 is d, so all of the d orbitals are here, and there is no 1d or 2d. L equals 3 is the f, so again all of the f orbitals are here. There's only one that's pictured here. We have just a 4f. We have no 1f or 2f or 3f, but there is a 5f that isn't pictured, a 6f and 7f, and so on, going all the way up to infinity. But what the Aufbau principle is saying is that when we go to add an electron, we're going to put it into the lowest available state. So as long as the orbital isn't filled, we're going to put it into 1s. When that one gets filled, we're going to put in the next lowest, which is the 2s, and then the next lowest, the 2p, and so on, going up from there. So on this diagram, the 7s would be the last orbital to be filled. So now let's look at Hund's rule. So Hund's rule says that when we fill a set of degenerate orbitals, now remember, degenerate means that they're at the same energy level, they all have the same energy. So this is something like the 2p or the 3p, 3d, something like that. So when we fill a set of degenerate orbitals, the lowest energy configuration for an atom is the one having the maximum number of unpaired electrons. What does that mean? That means that all of the degenerate orbitals get one electron in the same spin state. So by convention, we put them all spin up before any of the degenerate orbitals gets a second electron. So when we go to fill in a set, so let's fill in, say, the 3p. So when we put one electron in, we're going to put it in that first one. Again, it doesn't really matter which orbital we put it in, just by convention we put it in the leftmost one. When we put a second electron in, we're not going to put a spin down in that same orbital. It's actually slightly lower in energy to put another one in spin up. And the reason for that is similar to when you put two magnets close together. It's more energetically favorable. They tend to want to be opposite orientation, right? Well, here there's an energetically favorable position of having them aligned in the same orientation. So when we go to put that third one in, it will also go spin up, and then we go back and start putting electrons in spin down. And again, by convention, we start at the leftmost within that set. So we go spin down, spin down, spin down. So we can get up to 6 electrons in our 3p. And again, the first 3 get filled in into empty orbitals, and then we go back and we start filling in. So until each orbital is half filled, we put it in an empty one. Then when they're all half filled, then we go back to the first one again and start filling in. Again, by convention, spin down, although physically it doesn't matter whether it's spin up or spin down. So over here, you can see another diagram that shows, this is sort of the Aufbau principle laid out graphically. So remember that the Aufbau principle says we fill in the lowest energy orbitals first. Well, that's the 1s, and then the 2s, and 2p, and 3s, 3p, 3d. But wait, the 4s is lower in energy than the 3d is. So after the 3p, then we fill in the 4s. Then we go to the 3d, then the 4p, and then the 5s, then the 4d, then the 5p, then the 6s, and then the 4f, and 5d, 6p, 7s, and then we would get to the 5f, and the 6d, then the 7p, and so on. So we're not just going in the 1s, 2 SPDF, 3 SPDF, and so on. It's unfortunately not quite that simple. So here's a little graphic showing how they fill in. So if you write out 1, 2, 3, 4, 5, and then SPDF, if they have those, so there is no 1P, 1D, 1F, so it's just 1S, and the next line has 2S and 2P, the next line has 3S, 3P, 3D, the next line has 4S, 4P, 4D, 4F, the next line, the 5, has 5S, 5P, 5D, 5F. It would have a 5G, but we don't really need to write the G, so from here down, you can go down to 7 or 8 and get just right through the F. And then we draw diagonal lines through. So we draw one diagonal line, and we start at the upper right, and we go down. So whichever orbitals we hit first, that's the one that we fill in. So we fill in the 1s first, and that's the only thing on that line. So now we fill in the next line. Well, the next line is the 2s, so that's the one that we fill in. There's nothing else on that line. Then we get to the 2p, we fill in that one. Then we fill in the 3s, and there's nothing else on that line. Then we fill in the 3p, and then the 4s, there's nothing else on that line. Then we fill in the 3d. So now, again, you see we filled in the 4s before filling in the 3d, just like we did over there. And now we get to the 4p, and the 4s, and now we fill in the 4d, then the 5p, then down there is the 6s, and then we get to the 4f, and the 5d, the 6p, the 7s, and then back to the 5f again. And so if you can generate this diagram, then you know at least the order that we fill things in this diagram. You don't have to memorize how far apart they all are over here. Alright, so this brings us now to the electron configuration. So the electron configuration is a list describing, not graphically, but in letters and numbers, a list describing the occupied orbitals in an atom. So, for instance, the electron configuration for oxygen is 1s2, 2s2, 2p4. So if we draw that over here, oxygen has 8 electrons. So let's fill in those electrons one at a time. We fill in that first electron into the 1s. It's spin up. So we put that there. Well, we have no other degenerate orbitals. So we fill in the next one, spin down in the 1s. The next electron, that third electron, goes into the 2s, spin up. Again, it doesn't matter whether we put it in spin up or spin down, just by convention we put it in spin up. And then we have no other degenerate orbitals, so we put the next orbital into the next electron in the 2s, spin down. Now we have some degenerate orbitals in the 2p. And again, let's see, how many electrons do we have left? We needed 8 electrons total. We filled in 2 here and 2 there, so we have 4, so we need 4 more. So we'll put 1 electron in the 2p facing up. Then the next 2p orbital, again up, spin up. And then the last one, spin up. And now we have 7 electrons. But that's still not enough. We need 1 more electron. So we're going to put it in that first 2p orbital, spin down. Again, physically, it doesn't matter which one we put it in. But just by convention, when we're filling in our Aufbau diagrams, we put it in the leftmost orbital first. So, now, our electron configuration is a way of listing out what we have shown here, but without having to draw it out and take up quite as much space. So, we have 2 electrons in the 1s, so we label that 1s2. So, note that that 2 is a superscript on the s. So we have 1s2, we have 2 electrons in the 2s, so then we'll write 2s2. And now we have 4 electrons in the 2p, so we'll write 2p4. So altogether we say this is 1s2, 2s2, 2p4. Now, we could get more electrons into the 2p, we could get 2 more in there to get it up to 2p6. And then past that, well then we have to put an electron in the next lowest energy level, that would be the 3s. So, for a neutral gold atom with 79 electrons, the electron configuration is here. I'll draw out very quickly, fill in the Aufbau diagram for the gold. Note that I've incorrectly filled in the 4p before I filled in the 3d, but I know that they're all going to get filled in. So now we go to 4d, fill them all, spin up, before we go back and fill them in, spin down. Now we're going to fill in the 4f. So let's see, do I have 79 electrons yet? Not yet. So I need to keep filling. I need 9 more electrons. So I'll put 5 in, spin up into 5d, and now spin down. And now, note that I've put 4 spin down. I've left that last one with just that spin up. So now you can go through and count, make sure that I've done it correctly. I should have 79 electrons in there. So you can count up all the arrows that I've drawn, or you can draw it yourself and count up your own. And now let's list out the electron configuration. We have 1s2, we have 2s2, we have 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d9. So let's make sure that that's what I have written there, and it is. Now, that gets rather long. We don't want to have to write out all of that every time. Because as we go to the next element, well, now we're going to have 80 electrons, and we're going to have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10. And the next one will have all of that plus 6p1. So it gets rather cumbersome to write out all of these every time because we're just writing the same things over and over and over again, just adding one more electron on to the last term or adding one more term on. And so we want to be able to have a shorthand notation for this. So the shorthand notation for electron configuration, so note that on the last page, this is the full, complete electron configuration. So if I ask for the complete electron configuration, or if you're doing a problem that asks for the complete electron configuration, you have to write out all of them like this. If it doesn't ask for the complete, then, at least for my class, I'm perfectly okay with you using the shorthand, again, as long as it doesn't ask you for the full electron configuration or the complete electron configuration. So the shorthand notation is the electron configuration for an atom can be shortened by writing the symbol for the previous noble gas in square brackets, followed by the remainder of the electrons. So the electron configuration for gold, instead of writing out everything that we had earlier, we could write xenon, the symbol for xenon, xe, in brackets, and then tack on whatever xenon doesn't have. So xenon ends here. Xenon is all of this stuff that I've put in square brackets, the 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6. That's where xenon ends. And then the rest of this is what we have to tack on with our shorthand notation. So we write the xenon plus 6s2, 4f10, 5d9. And that way it's significantly shorter, and we don't have to write all of that other stuff that's all encapsulated in xenon. So note here that the electron configuration of a noble gas should never just be written with its own symbol in square brackets. You have to use the previous noble gas. So if we want to write xenon's electron configuration, we have to use the previous noble gas. We can't just write xenon in place. All right, so now we want to differentiate between valence electrons and core electrons. So valence electrons are electrons that are in the outermost occupied energy level. So this is the principal quantum level, so the outermost n value. Core electrons are inner electrons. So those are the electrons that are not valence electrons. So in chemistry, the interesting stuff occurs in interactions between one atom and another atom. Well, those interactions are always occurring between the electrons that are on the outside. The electrons on the outside are the valence electrons. The core electrons are too deep in the atom. They basically are not involved in the chemistry of the atom at all. So the valence electrons are the important ones. Those are the ones that we as chemists are really interested in. The core electrons are just sort of filling up the orbitals, taking up space. The valence electrons are really the important ones in the atom. So, but again, this is the outermost occupied energy level, because all atoms have an infinite number of energy levels. So the valence shell, the valence electrons occupy that outermost occupied energy level. So when we remove electrons, if we remove enough of them that now there are none left in what was the valence shell, now the valence shell is the next shell down, and now it would presumably be full. So let's look at fluorine, and we want to figure out how many valence electrons fluorine has. So we know that fluorine has 9 electrons, so when we go to fill in, we put one in the 1s, put the second one in the 1s, spin down, we fill in the 2s and the 2p, and let's see, now I've put in 2 here and 2 there, so 4, I've put in 7 total. We need 9 electrons, so I need to add 2 more, spin down in here, and now I'm done. So note that the 2p is not full. We can get 1 more electron in there. So, how many valence electrons does fluorine have? Well, remember that's the outermost occupied energy level. And you might be tempted to say 5, because we have 5 electrons in the 2p. But you'd be wrong, because energy level means n, right? Because it's the principal quantum number. So the n value there is 2. So all of these electrons count. Those electrons in the 2s, even though they're at a slightly lower energy than the electrons in the 2p, they're still in that second energy level. And so those 2 count and these 5 count. So fluorine has 7 valence electrons. How many core electrons does it have? Well, it has 9 total. 7 of them are valence. The rest of them, those 2, must be the core electrons. So we have 7 valence electrons, and we have 2 core electrons for fluorine. So now let's look at how many valence electrons iron has. Well, iron has 26 electrons total. So we're going to fill in 2 here. We're going to fill in 2 more there for 4. We'll fill in 6 here for a total of 10. Now I'll fill in the 3s. Now we have 12. We'll fill in the 3p to get us up to 18. We'll fill in 2 more in the 4s. So now we're at 20. We still need 6 more. So let's put them into the 3d. That's a poor looking arrow. So we've got 6 electrons in the 3d. And let's see. How many valence electrons do we have? Now, the last electrons we put in went into the 3d. So again, you might be tempted to say 6 valence electrons. Or you might be tempted to say, well, 3, and so 6 plus 6 plus 2, so 14 valence electrons. But that's not how many valence electrons iron has. Because again, remember, it's the outermost occupied principal energy level. So we have electrons in the 4th energy level. So that 4th energy level, that's our valence shell. So those electrons in the 4s, the 4p, the 4d, and the 4f, which aren't pictured here, those ones count. We only have 2 electrons there. And again, if we write out the electron configuration here, we have 1s2, 2s2, 2b6, 3s2, 3b6, 4s2, 3d6. But that 4s2, those are the ones that are on the outside. These 3d electrons are closer into the nucleus than the 4s are. So the 4s electrons, those are the ones that are on the outside. Those are the ones that are going to be involved with the chemistry. Those are the valence electrons. So iron has 2 valence electrons. It doesn't have 6 or 14 or a combination, so 16. It doesn't have that many valence electrons. It has 2 valence electrons. Right? So only the electrons that are in that outermost n that outermost principal quantum number, that outermost energy level, those are the only ones that count for valence electrons. So, what this means is that if we have hydrogen or helium, right, if we're in that first period on the periodic table, we can have up to 2 valence electrons. In periods 3 or 4, we can have up to 8 valence electrons. And after that, well, when we fill in here, in these transition metals, we're filling in the D subshell of the energy level below. So here we have 1 valence electron, here we have 2 valence electrons. In all of these, with just a few exceptions, we have 2 valence electrons. And then here we have 3 valence electrons, 4 valence electrons, 5 valence electrons, 6, 7, and 8. And down here we all have 2 valence electrons. And I'll sort of explain why these guys only have 2 a little bit more. We talk more about the periodic table. So the periodic table, again, looks like what was on the last slide. Within each box on the periodic table, we have 1 element. We've got a symbol that is specific to that element. So we always have, that's called the atomic symbol. So we have 1 or 2, possibly 3 characters, but usually 1 or 2. The first letter is always capitalized. The second letter is always lowercase. So if you write this as capital M, capital O, that's no longer molybdenum. That now is, well, the O now stands for oxygen. The M, there is no element with just a capital M. We usually use that to denote a metal of some sort. And so that's no longer molybdenum if you don't write that O lowercase. So you need to be very careful with how you're writing your atomic symbols. So up the top we've got an element name. The exact placement of the name can vary some. The atomic number is always written up towards the top. Sometimes it's in the middle, sometimes it's towards the left. The atomic number is how many protons we have. Again, that's Z. And then at the bottom we have our atomic mass, which is symbolized A. This is an average mass that's listed on the periodic table. And we'll get back to why that's an average and not an exact number. So the periodic table is arranged in certain ways. We've got certain sorts of collections of elements. We have periods, which are the horizontal rows on the periodic table. So we've got the number, so this is period 1, that's period 2, 3, 4, 5, 6, and 7. So hydrogen and helium are in period 1. Period 2 is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Period 3 is sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, and so on. We get down here to period 7. You notice that on my periodic table here, we don't have symbols in there. On a newer version of a periodic table, we would have some symbols in here. We've actually discovered all the way through element 118 as of the recording of this video. They aren't all named. So most of these, I think we've tentatively named a couple of them. I don't recall what the names are offhand, but the rest of them are have been given temporary names that are they're basically the atomic number. So it's unium for 111, for 111, dium, and so on, going all the way up to octium over here at 118. So again, the periods are the horizontal rows. These 2 rows down here, those are not periods. These really belong in here, and I'll get to that again in a little bit. So the groups are the vertical columns on the periodic table, and we have throughout time used 2 different systems for describing these. The one that I use is to label this group 1, and that group 2, and this group 3, 4, 5, and so on. Which means that now we get back up here to group 13, and then 14, 15, 16, 17, and 18. So we have groups 1 through 18. So everything in this column, that's all group 1, this is group 2, and so on. Over here, the noble gases are group 18. Again, note that these guys down here are not part of any of these groups. Right? So, lutetium here is not in group 18, and cerium is not in group 5, and so on. These guys, again, don't belong here in the groups. That's why there's this space here. The other system was to label groups 1 and 2 the same, but these were labeled 1A, 2A, this was 3A, 4A, 5A, 6A, 7A, 8A, so basically these numbers just minus 10, and then all of these guys, the transition metals, were labeled with B's on them, and but I don't use that system. I like numbering them 1 to 18. So let's go back one moment here to the groups. So the group, within a group, the chemical properties are similar. Not exactly the same, but similar in that over here we have the noble gases. Those all act about the same way. They don't react with anything for the most part. Under very, very special circumstances we can get them to react. We used to call them the inert gases, but we've since found very, very special cases where a couple of them will react to form compounds, and so now we call them noble gases because most of the time they don't react with anything. And something like like this group here, group 17, those all act similarly. We call those the halogens. So we've given some of these groups special names. So the first group here, not including hydrogen, but everything from lithium down, those are the alkali metals. Group 2 are the alkaline earth metals. Groups 3 through 12, those are all the transition metals. Group 18, again, is the noble gases. 17 are the halogens. 16 is sometimes called the chalcogens. And then these three groups, we've given the ridiculously original names of boron group, carbon group, and nitrogen group. And down here, these are not groups, but we have some series. We've got the lanthanide series here, given by the name of the first in the series, lanthanum, and the bottom row there is the actinide series. Again, they're not groups because they're not vertical columns. They're series because they move across the periodic table. So, we have metals, metalloids, and non-metals on the periodic table. So let's look at the metalloids first. The metalloids have properties sort of in between those of the metals and the non-metals. And if we draw a staircase here, starting between boron and aluminum, and we go down and to the right, and continue going down and to the right, the elements that border these, with the exception of aluminum, so sometimes boron, silicon, germanium, arsenic, antimony, tellurium, polonium, and astatine, those guys are all considered the metalloids. And again, those have properties in between those of the metals and the non-metals. Now, everything on, let me go to the next one, I'll draw in my staircase again, and everything on the left side, so the bottom left, so everything over here, so from gallium and tin and bismuth, all of these elements over here, up to beryllium, not including hydrogen, hydrogen is a non-metal, and all of these guys down there, those are all the metals. Right? So these all have somewhat similar properties in that they act metallic. They form metallic bonds within the element from one atom of that element to another atom of the element, and so on. So they all have certain properties. They're all generally conductive. Then we have the nonmetals. Again, I'll draw in my staircase there. Again, remember the staircase starts between boron and aluminum and goes right and down. So the nonmetals are all on the upper right-hand side of that staircase. So carbon, phosphorus, selenium, and iodine, radon, and up. So all of the noble gases, the halogens with the exception of astatine and so on, those are all nonmetals, plus hydrogen over here, that's also a nonmetal. So there aren't nearly as many nonmetals as there are metals. Again, we have the lanthanides and actinides down here. Now, the periodic table has sort of this weird shape to it, right? And the periodic table's strange shape arises from the filling of electron energy levels. So the orbitals, the subshells, the s, p, d, and f. So we have blocks on the periodic table corresponding to our s, p, d, and f suborbitals, our subshells. So these are this is the orbital that our last electron that we filled into our atom went into. So if we look up here, we have 1s. So hydrogen and helium fill in the 1s. Note that this first period is a little weird. So then we have lithium and beryllium. Our next two electrons go into the 2s. Then we have 6 electrons go into the 2p. Then we have 2 electrons go into the 3s, and so on. So these two columns, this is the s block. And again, remember that helium kind of belongs over here because we're filling in the 1s, but it belongs over here chemically because it's a noble gas. And so we've put it over there, but really it's kind of part of the s block. So then we have over here these guys. So again, note that I'm not including helium and I'm not including the lanthanides or actinides here. This is the p block because we're filling in the 2p or the 3p or the 4p or 5 or 6p and so on. Now in between the transition metals, all of these guys, here we're filling in a d block. Now note here that we're filling in a d block of the energy level below the period that we're in. So here we're in, so for titanium, let's say, we're filling in the 4s, but then we go and fill in the 3d. Here we're in the 5th period, we filled in the 5s, and now we go back and fill in the 4d, and so on. So this is the d block, those are the transition metals. And then down here, we have the f block. So our lanthanides and actinides, that's our f block. And you notice that each of these has a different number of elements wide in them. So the s orbital holds 2 electrons. We have 2 elements in our s block. The p orbital, the p subshell, has 3 orbitals holding 6 electrons. We have 6 elements in our p block. The d subshell can hold 10 electrons because it has 5 orbitals, and we have 10 elements in the d block. The f orbital holds 14 electrons because we have 7 orbitals, and so we have 14 elements in the d block. If we had a g block on the periodic table, which we don't, but if we at some point in the future discover enough elements, make them, to get to a g block, then we would have 18 elements in the g block because we could get up to 18 electrons in the g block, in the g orbital subshell. So that f block really belongs here in the periodic table. So if we spread out our periodic table, move our lanthanides and actinides up and stick them in here, we really have now our 2 elements for the s block. Again, note over here that the helium really should be over here as part of the s block, but again, it's a noble gas, so we put it on that side of the periodic table. Then we filled in 1 electron in the d subshell, and then we go back and we fill in the f subshell. It's a little complicated to explain why that occurs, but we've stuck our f in there, and then we continue our d, and we've put our p block in over here. So really the extended periodic table, the periodic table really should look this way, only that gets even wider than it currently is, and that means the font would have to be even smaller when we write it all on one page. So we've pulled this section out and moved it down to the bottom. They're not terribly common. Most of them are man-made anyways, and so most chemistry classes we don't use these guys down here too much. Uranium is usually the highest that we go to. So that was the Aufbau principle and the periodic table.